Animation can help us visualize what's happening with these volumes by revolution. Consider this quick curve here, y is equal to the square root of x, and we're interested in between these two values, a and b. I'm looking for just 5 rectangles, so that's why we see n is equal to 5 right here. And we're revolving this around the x-axis, which is when y is equal to 0. Right? So here's one of the rectangles, and if I revolve that one rectangle, like so, you can see that what I'm really creating here is a cylinder. All right, it's a bunch of circles on top of each other. And the idea is that we would revolve all of them. So we have those 5 right there. Now those 5 are, if we put them together, they're sort of starting to create that solid that we're looking for. All right, now what's better than 5? Because obviously we can see right up here where I've got the cursor, we're at too large. Well, what if we change this 5 to a 50? All right, and if we do that, well, let's see if we show. Now when we have a much skinnier cylinder, so hence it's a disk, and then we got our disk method, and if we see them all right, well now we're really filling things in rather nicely, so you can get a better idea of that solid right there. So when we get to example number 11, we're looking at let me just get to the right one here. There we go. We have the function f of x equal to x squared, and we're interested from 0 to 2. So when we revolve this turquoise region right here, we're getting, excuse me, that almost like a top on its side there, or a tornado, that type of deal, where we can find the volume of this because we're just looking at, we get that one circle, that one disk in there, and if we add up the areas of all those disks, in essence, we're getting our volume going. All right. If there are 2, let's go to this one right here. All right, this is going to be connected to the washer method, which you'll see as we get closer to example number 13. Here's the visualization of the washer method, where we're revolving this region between these two zones around the x-axis. So now it's hollow in the middle. We're getting, in essence, like our satellite dish, where it still has a volume, but there's the opening on the inside right there. All right, so we have to subtract that inner part. So we're going to have to use our knowledge of the volume, rather the area between two curves, and kind of connect it to our volume. And not only can we go around the x-axis, but we can also go around the y-axis. Where's that one? Come on, get this out of the way here. Right here. Here's the same two curves, but this time when we go around the y-axis, all right, now we have this situation right here. We're actually creating a glass, a water glass, if you will. We can find the volume of glass that's needed to create this. We can also find the volume, if need be, of the amount of water that this would actually hold. As we create this glass and we find the volume of the actual glass that's needed to come up with our actual design right here, keep in mind, though, we are going around the y-axis. So our little differential is going to be a little bit of y, and therefore we're going to need to have our functions, as you can see right up here. Our functions need to be in terms of y, and our bounds need to be in terms of y as well.